What is a wormhole? Okay, we were trying to get to that, to this thingy that the mathematicians talk about. They research it. They do a lot of equations out there. Um, are we wasting our time and money? Time is money, right? So are we wasting our tax money on researching wormholes? What is this about? Is this just for Hollywood movies? So we say, hey, we're going to travel through a wormhole to another universe and blah blah blah. You know, great fantasy. But they say it's not fantasy. It's science. Is this science? Does this belong in science? Do we have to have any mathematicians on planet Earth working on this stuff at all, or even thinking about it, or even pondering it as even a remote possibility? That's the issue. I mean, is this wormhole something we even have to talk about in science? Is it? Do we even have to criticize it? Well, let's find out where we stand. We've been doing lately the universal movie to different concepts, and we're going to have to apply it to the wormhole. So, what is the universal movie? Let's start there. A little quick introduction. Most of you are familiar with it, but for new arrivals, they probably don't know what I'm talking about. So, let's go quickly through that. Here we have the universal movie, and what we're saying is all static concepts fall in a single frame of the universal movie, whereas all dynamic concepts, the ones at the bottom, they require at least two frames in the universal movie. Now, this is a little different than what general relativity has, okay? Both special and general relativity for that matter. And in fact, it's throughout the mathematical world, okay? And they have to have this notion that time is not the same at the other side of the universe as it is over here. So they don't like, they're not against, they're not in favor of this universal movie idea. They don't know about it, but if they heard about it, they would not be in favor of the universal movie. Why? Because they say it depends on how you measure time. And of course, someone over there is going to measure time different than someone over here because they have different vantage points, okay, different reference points. They're traveling at different speeds, so their measurements are going to be different. We don't care about any of that. That's all nonsense. The universe, every atom in the universe only has location in one frame of the universal movie. From there, it moves to the next frame of the universal movie, and people say, well, but there's a itinerary in between. Absolutely not. We're going to chop that itinerary as much as you want until we get almost no motion at all. We're talking about frames in the movie. Every atom in the universe just moves to the next location. And motion is built through location. Motion is two or more locations of an object. And what is the location with respect to? All other matter in the universe. So every frame in the universal movie only has location, a static concept. There is no motion in that frame. So all this nonsense about special relativity, how you measure and how I measure time, and for you it's faster, for me it's slower, my clock ran faster, yours ran slower, we don't care about any of that. That's all poppycock, nonsense. It's hogwash, okay? So yeah, the universal movie destroys this notion that there's different times in the universe. In fact, we don't care about time. We talk about location, a static concept. And we go from location to location because that's what motion is. If you don't like the definition of motion as two or more locations, you have to provide a definition of the word motion. You have to tell us what motion is, and not like Mr. Newton said, I don't define motion because everybody knows what it is. Yeah. And to this day, nobody has defined the word motion. They define it as change, and change is motion. So change is just a synonym. That's not a definition. We can't use the word change to define the word motion. Okay, we say two locations. That everybody understands because we have two static concepts transform into a dynamic concept called motion. Okay, so here where we put dimensions, something that we're going to talk about today. Lately we've been talking about these, and we said, look, dimensions and coordinates are static concept, whereas what the mathematicians use, which is number lines, are dynamic concepts. Why? Because a number is the verb to count. That's what the word number means. It's to count. We also have vectors at the bottom. Why? Because a vector is a concept that has something moving from A to B. It's a displacement, and that's what we call vector. Okay, and there are three ways in which you can move from a given point. They're all perpendicular to each other, orthogonal, and they're depth, breadth, and elevation. Those are the three vectors. Okay, depth, breadth, and elevation, and all of those involve motion. Okay, so that's why vector is a dynamic concept, whereas coordinate, which is about location, and dimension, which is how something is pointing or facing, both of those are static concepts. Okay, we have to get that straight because we ended up with these black holes that we discussed the other day, the zero dimensionality, the world of the 0D. Is there such a world? Is that a dimension called the zero dimension? Okay, and where did we put that? Well, we don't know where to put it because really a singularity and a black hole are both concepts, but they treat them as physical objects. They're not. They're concepts, and so we have a problem because if they're objects, if we're going to treat them as objects, they're static objects. A black hole does not need to move. It's just something out there in the sky, okay, that supposedly has location with respect to us. The problem comes in that both the black hole and the singularity are 0D, okay, as we explained the other day. And if they're 0D, they're not objects. And so the problem here is that we have a contradiction between whether a black hole and a singularity are objects or concepts. Okay, so this is where the problem is. But if they are objects, we have to put them as a static object. Neither the singularity nor the black hole move. In fact, we cannot imagine a 0D moving anywhere because a 0D is not an object. So we need two locations of an object to create motion, and we don't have an object to begin with. So, I mean, how are you going to move a 0D nothing from A to B? You have nothing. What moved? That's the issue. Okay, so what's the issue? The mathematicians, because they have never defined what a dimension is in a scientific way, they never defined what a coordinate or a vector is in a scientific way, they confuse them with number lines. Because of that, they ended up with irrationalities. They ended up with multidimensional universes. And here you have a rundown. Okay, this is the multidimensional world of mathematics, mathematical physics. We have the 26-dimensional world of string theory, known as bosonic string theory. We have 11 dimensionals of M theory, brains, 10-dimensional superstring theory. Okay, those are all from string theory, and they have to have all these dimensions in order to explain gravity or somehow merge quantum mechanics with general relativity. Okay, the world of particles are very small, with the macro world of cosmic, the universe. Then we have the Kaluza-Klein theory from 1921, 5-dimensional universe. Okay, they need 5 dimensions to explain how this universe works, otherwise it wouldn't work. Then we have the 4-dimensional one that people like Einstein came up with. He wasn't the first one. Even before that, you have Minkowski and Poincaré and so on. All these people already had come up with these ideas. Einstein simply took the credit for it. We have the 3D Euclidean world that comes from Euclides, Greek philosopher, whatever he was, just a guy who tried to do some geometry. Okay, the 2D world of Euclidean geometry, the planes. Then we have the 1D line. They call it the 1D line, but there's no such object, no such geometry as a 1D line. The 1D is not an object, it's not a figure, as we explained the other day. Okay, so there's no such monster. Turns out the wormhole, as we're going to argue today, is 1D. We're going to get into that. And then we have the 0 point, zero-dimensional point. What is that? Well, it's nothing. But they say that's what a black hole is. That's what the singularity at the Big Bang was. It was nothing. Okay, 0D is nothing. It's a definition of nothing. Okay, so let's find out how what we're going to do with this. We've got these dimensions. Here we have one fellow who you can see why it confuses people like this gentleman here who Also got confused because the mathematician never defined dimensions and coordinates and vectors, and so he uses these words. You can see here how he's going to use them, and it shows that he's got a lot of influence from the mathematicians, and he was simply brainwashed by them. Here's you can see it here. Okay, speaks for himself. It says graphene is composed of a single layer of carbon atoms arranged in a two-dimensional honeycomb lattice. It is a fundamental building block for a range of well-known carbon materials such as three-dimensional graphite, one-dimensional carbon nanotubes, and zero-dimensional fullerene. Okay? So where does he get all this stuff? Well, again, he's using these words from mathematics. He's not talking about dimensions. He's talking about number lines, okay, not about dimensions. He's not talking about length, width, and height, which belong to physics. He's talking about number lines, and those don't have direction. Number line does not have direction. They put an arrow because they say numbers increase in that direction, but there is no direction. You can put numbers in any way you want. You can put them without a direction. Okay? The 2 is not in front of the 1, and the 3 is not in front of the 2. You can put them in any way. You can put the 3 behind the 1 and the 2 in front. You can do whatever you want with numbers. They have no location. Okay, and so it's when you put them in a line that it confuses people. They think they're talking about a line, which is what, one-dimensional? Please draw it. And then he says the two-dimensional motions. Two-dimensional motions. No, motion are not dimensional. Okay, you can talk about vectors, maybe number lines, but you cannot talk about two-dimensional motions. No such monster. Okay, so where did wormholes come out of originally? I mean, how did we end up with one-dimensional wormholes? Who came up with this nonsense? Okay, and here we have a famous fellow. His name is Hermann Weyl, okay, or Weil in German. He's the inventor of the topological idea of wormholes in space-time. He was a student. He was a person who studied Einstein quite in detail. He wrote a couple books regarding general relativity. So he's one of the head honchos in those days in the 20s, okay, of general relativity. He pushed for general relativity. Weyl spoke of one-dimensional tubes. Well, when I think of a tube, I think of a cylinder, you know, like a hose maybe or something like that, you know, and this is not what he's talking about. One-dimensional tube, like a contradiction in terms. What kind of tube is a one-dimensional tube? Please draw it. Okay, and this is where we have problems with what these people say, because they say one-dimensional tube, nobody challenges that, and they get away with murder. That's what's happening. Okay, inside these tubes, no space exists. First of all, space cannot exist because space is not an object, and only objects can exist because the word exists is an object that has location. So he's using the wrong notion of exist. He's got to define the word exist before he can use it. And he's just saying that it exists or doesn't exist. No, space cannot exist. Space is nothing. Nothing does not exist. It's objects that can exist if they have location, not space, which is not a thing, and therefore has no location. Okay? So again, we see the faulty language that all these mathematicians use, and that's why people get confused out there. And their boundaries are analogous to infinite distance, inaccessible. So what they do, they put it beyond your grasp. They say it's infinite. It's at infinity. Go over there. And so you say, well, I'm not going to go over there. I'll just accept it. And that's what they do. They accept it on the basis of authority because the guy used the word infinity or infinite. Okay, that's how they get around these things. Okay, wormholes thread through space as air channels through Swiss cheese. Okay, so Swiss cheese has all these holes. So what do they explain? They're explaining tubes going through this cheese, right? Space having all these holes through it, and they're one-dimensional tubes. We cannot even picture what these people are saying. They cannot picture it. They cannot draw it. Okay? But they get away with murder. Electricity is not electricity. Electricity is electric lines of force trapped in the topology of space. Okay, so we have electricity in there. Somehow it's these holes in space. Okay, Weyl did not use the term wormholes. It was John Wheeler who later coined the term wormhole in 1957. Okay, so yeah, um, Herman Weyl did not come up with that, but he had the idea, okay, the idea of the wormhole already. And here's how he defined it essentially. Einstein's spatially closed universe is often referred to as Einstein's cylinder world, with two of the spatial dimensions suppressed. Okay, so they take length, width, and height. That's what they're talking about. Okay, they're going to remove two dimensions. They're going to leave length or width or height, one of the three, right? But look what they say. They suppress two dimensions. The model universe can be pictured as a cylinder with one dimension, okay, where the radius A represents the space. Radius? What radius can you have with one dimension if you took two dimensions out? And the axis, the time coordinate. In other words, what is that single axis? It's time. And that's what Weyl was thinking about when he was thinking of his famous wormhole. He didn't call it a wormhole, but that's what he was referring to. He was referring to one-dimensional, what? Time. What is time? Is it a dimension? No, it's not a coordinate. It's not a vector. It's a number line. That's what time is. It's not a dimension as mathematicians want you to use the word to define it or to characterize it. Okay, so we're talking about time. That's what the wormhole is. It's time. And here you have another vision of that, okay? You have this wormhole that they say you can cut across space by thinking of space as something that's curved around, okay? And they're going to have time go through this from one place to another, shortcutting the trip around that whole region there. So they're just going to have you moving through this so-called wormhole. And what is that wormhole? You're traveling through time. You're traveling through one-dimensional time, meaning a number line. They're talking about, a number line. You're traveling through a number line, a one-dimensional number line. They're not talking about anything that's thick. They're saying it's a tube, but the tube is one-dimensional, and they're referring to time. So yeah, it's very, very confusing, okay, because they cannot illustrate what they're saying. That's the issue. They cannot even imagine what they're saying. That's the whole point. Okay, so what is the definition of a wormhole? Is it a thing? Is it an object? Well, here you have wormholes. This is one fellow who, I think this is out of the Wikipedia. It says, space can be visualized as a two-dimensional surface. Not true, because space is nothing. So it's not a surface, and it's not two-dimensional, and you cannot visualize it. Space is absolutely nothing. We take all the atoms from the universe away somehow, we have absolutely nothing in front of us. In this case, a wormhole would appear as a hole in that surface. So here they create a two-dimensional flat surface. Think of it a piece of paper, even though it's 3D, but try to think of it as a flat sheet of paper, okay, completely flat, and you're going to put a hole in there. So now you're looking at it from the top, and you're saying, well, that's a surface now, okay? So you're looking at the hole from above, and you see a surface, okay? Lead into a 3D tube. I thought it was a 1D tube. Now they turned it into a 3D tube. The inside surface of a cylinder. Yeah, a cylinder is 3D, but that's not what wormhole is. Wormhole is 1D, as Mr. Weyl told us, okay? And that's also what Einstein referred to when he created this monster. Then reemerge at another location on a 2D surface with a hole similar to the entrance. In other words, they're referring to black holes. They're saying that the ends of a wormhole are 0D singularities. And those are the centers of black holes. Okay, so we have a wormhole that's connecting two black holes. One is in, I guess, one universe, the other one in another universe, or different points of space, or however you want to think of them. Okay, and as you can see, it's so realistic what they're showing you there. But people love to draw wormholes. I mean, you've got millions of people out there drawing wormholes because they absolutely love the concept. Okay, and they try to illustrate, and they're illustrating poppycock. That's what they're illustrating. They're illustrating something which has no possibility of even being real. Okay, an actual wormhole would be analogous to this, but with the spatial dimensions raised by one. What do you mean spatial dimensions raised by one? For example, instead of circular holes on a 2D plane, the entry and exit points could be visualized as spherical holes in 3D space leading into a four-dimensional tube similar to a spherindor or spherindor. Okay, what's a spherindor? Well, it's a geometric object, they say, okay, defined as the Cartesian product of a three-ball or a solid two-sphere, whatever all that nonsense means, of radius r1 and a line segment. The line segment, what is that? That's going to be time. So it's not a line segment. They're talking about time, which is a number line. It's not even a line. Like the duo cylinder, it is also analogous to a cylinder in 3 space, which is the Cartesian product of a disk with a line segment. Okay, let's find out what a duo cylinder is. It's a geometric object, again. It is it? Embedded in a four-dimensional Euclidean space, defined as the Cartesian product of 2 disks. Well, all the images that you see on the right, which apparently are the wormhole, the spherindor, and the duo cylinder, as you can see, they're all 3D projections onto 2D surface. So all the images are 2D, but they're trying to project a 3D image onto a 2D. None of those are 4D. And you cannot illustrate the 4D that these people are trying to explain in a roundabout way. In fact, even the famous warped space-time that mathematicians dealt since the days of 1915 or even earlier, even that is 3D. All of these images are 3D projections onto 2D. None of them are 4D, and you cannot even imagine the 4D, let alone picture it, illustrate it. You cannot depict it. Okay? You cannot draw an image of a 4D, no matter how you try. In fact, if it's got time embodied in it, you're talking about motion. So you're not talking about a static image like a table or a rock. You're talking about something in motion. When you stop it, meaning no time, what you have is 3D. 3D. You have the table. So they're saying a table that moves is a four-dimensional table. That's what they're saying. And a rock that moves is a four-dimensional table because now you have to include time in what you're staring at. So you're talking about a movie, not about a static image that you can just illustrate. That's why they cannot illustrate the 4D, because it's got time in it. Okay, so here's another fellow, but he says that it's not an object like these people are trying to tell you, all these so-called objects. This fellow, he says that it's a mathematical concept and nothing but. And he's prominent in Quora, so you can find him very easily. His name is Victor Toth. I talked about him in the past. And he says the following about wormholes. He says, wormholes in general, relativity, are mathematically valid solutions of Einstein's field equations, the equation that describes gravity and curved spacetime, which connect distant regions of space. Okay, so he's saying that, look, it's just a solution to an equation. So this nonsense about, there being a tube out there in space connecting different points of space, that's nonsense. So he doesn't say it that obvious that he doesn't believe in this nonsense, but he just suggests, insinuates that maybe they don't exist. Of course they don't exist. It's because it's poppycock. It's nonsense. Okay, so here you have it. This is what the tesseract is, okay, which is another notion that they have for the 4D. And all it is just an expanding cube. That's all that the tesseract is. There is no such thing as a tesseract. It's not a four-dimensional object, because the only way you can present the tesseract is in motion, and you're talking about time. That's what those corner lines are. Those are indicating time. So none of the objects that these people present are 4D, and likewise you cannot present the 0D, which is the so-called singularity that's gave rise to the Big Bang or is in the center of every black hole. There's no such monster as 0D. And likewise, there's nothing like the 1D, which is what the wormhole is alleged to be, because the wormhole is just time. That's all it is. And time is a number line. And so they talk about dimension, they talk about tubes. Some call it the 1D tube, the others call it the 3D tube, because you can picture that, a cylinder, and people say, okay, I understood that. Yeah, you understood it, but you're not understanding. You're not understanding what the Einstein-Rosen bridge is. And so they went a step further, and it was Einstein and a couple of his buddies who came up in 1935 with two concepts that created a lot of this stuff. Okay, they expanded on Mr. Wales' notion, and they mathematized it. Okay, here it is. Einstein, Podolsky, and Rosen, they came up with EPR. That's what EPR stands for, Einstein, Podolsky, and Rosen. And they were criticizing quantum mechanics in 1935. They didn't like quantum mechanics, so they created this thing which today is known as entanglement. Okay. And a couple months later, Einstein and Rosen, they came up with ER, the particle problem in general theory of relativity, where they also, went in there and said, well, how do we handle things such as wormholes? And that's where the wormhole came into being formally with ER, okay? And so what happened since then? Well, we had these two individuals, one Maldacena, a person from co-national of mine, and another fellow, Susskind, those who know him, Leo Susskind from California, and they proposed the following. They said ER is equal to EPR. They're both the same, and it's what they call a conjecture, okay, in physics. And this is essentially what they're referring to, which is essentially the definition of a wormhole today. It states that two entangled particles, a so-called Einstein-Podolsky-Rosen or EPR pair, are connected by what? A wormhole, or an Einstein-Rosen bridge, which is the second paper that Einstein wrote that a couple months later, right? ER equal EPR is thought by some to be a basis for unifying general relativity and quantum mechanics into a theory of everything. That's why it's so important to these people. Because if they can say, look, a wormhole that goes through space and connects two black holes is pretty much like, the whatever that connects two particles during entanglement. This particle affects that one over there instantaneously. Well, a wormhole in space connects two wormholes instantaneously. And so it's a conjecture. Why? Because they haven't proven the existence of wormholes. They claim to have proven the existence of black holes, right? And so, they're working on this because of that. And Leo Susskind and Juan Maldacena in 2013 proposed that a wormhole is equivalent to a pair of maximally entangled black holes. Okay, so they're using these words to try to unite general relativity with quantum mechanics. That's why it's so important to them. That's why they're working on it. That's why they're spending your tax dollars on this nonsense. EPR refers to quantum entanglement, the EPR paradox. Okay, so this is what it looks like, okay? You can see there on the one hand you have EPR on the right, and you have ER, the Einstein-Rosen bridge, which is the wormhole. One is cosmic, and the other one is here in the lab. You can say that the one on the left has to do with general relativity, the one on the right has to do with quantum mechanics. And if they can get those united, well, you can see where they're going with all this. They're trying to make sure that you understand that what's between two particles is a wormhole. And what's between two black holes is a wormhole. What is a wormhole? It's a one-dimensional time, which is a number line. That's what they're talking about. So when you're traveling through a wormhole, you're not traveling through a 3D tube, cylinder. You're traveling through time. That's what they're saying. So that's what all this nonsense is all about. Okay, so where do we put the wormhole in our universal movie. Is it a static concept? Is it an object? Is it a dynamic concept? What is a wormhole? Okay, and here we have it. We put it as a dynamic concept. That's what they're referring to. Why? Because it has to do with time. Okay, so that's what the issue is. Wormhole is time. In fact, it's not having to do. It is time. Whenever they talk about wormhole, they're talking about time. Time is what? Is it one-dimensional? No, it's one number line. Wormhole is time. Time is a number line. That's all they're talking about. So when they say you're traveling through a wormhole, you're just traveling through time. Okay. Can we talk about holes in general? Like, and I'm not talking about those kinds of holes. Talking about, or nose holes, right? No, we're talking about black holes and wormholes. Okay. Can we talk about holes without there being something into which the hole goes, or through which the hole goes through? Okay, and that's the question. Here you have a groundhog hole. Okay, we all can relate to that. That's more or less what a groundhog hole looks like underneath the ground. Okay, it looks something like that. What if we were removed to remove the trees, and we remove the groundhog, we remove the ground, we remove everything except the hole? What would we have? Well, we would have something that looks like this. That's what a groundhog hole looks like without everything else. That's what a hole looks like. A hole is a concept. It's not a standalone object. So you will not have a something there, for you to see or touch or whatever. Okay, so there's no such thing as a hole. Hole is a concept. Okay, so what happens to a wormhole? Well, they show you something that looks more or less like this, and they say that's a wormhole. Everybody looks and says, yeah, I recognize it's a wormhole. But what is the wormhole through? Well, they say it's through space. Okay, the hole perforates space because you're going to go from one region of space to another. You're going to enter one black hole, zero-dimensional black hole, going to go through this tube, 3D tube. You're going to end, which is a hole, really, through space, and you're going to end up, or come out of a black hole on the other side of the universe, or maybe in another universe, for all we know. So if space is nothing, what is the black hole through? Well, here I'll show you. I'll illustrate that for you. Here it is. That's what it's through. That's what a wormhole looks like without space. Okay, because if space is nothing, the hole is absolutely nothing as well. Okay, so what can we say? This is what you're traveling through when you're saying that you're traveling through space. Okay, let me remove this little thing here. Okay, so what can we conclude? Wormhole is not a thing, so it's very hard to put it into a static concept because it's time, a synonym of time. So you're traveling through time, and so time is a dynamic concept. We would put it under the universal movie. Would put it together with the dynamic concepts. And then the other thing is that without space, you have no wormhole. The only way you can have a wormhole if space is something, if it's a thing. You can run a hole through Swiss cheese, as they were saying, or you can make a gopher hole if you have the ground. Without the ground, without the Swiss cheese, you have no hole. Okay, so let's get that straight first. And likewise, if a wormhole is through space, and if you remove space from the wormhole, you have no hole. And you don't have to remove space because space, by definition, is nothing, that which has no shape. There is nothing there. So it's as if you remove the ground from the groundhog hole, and it's if you remove the cheese from the holes in the cheese, Swiss cheese, right? Then you have no holes. And that's what happens to the wormhole. Wormhole is absolutely nothing, just like a black hole.